Okay. All right. So last time what we did was we derived some equations. We derived the forced Newton-Euler equations. I showed you them, and we looked at the forced Euler-Lagrange equations. And finally, the forced geodesic equations, and we saw that they were all equivalent to one another. Okay, so what I want to do today is just look at some examples. And finally, write down some equations of motion in their final and complete form. First, for our planar body example, okay, and so we had sorted out all the data. Okay, so we had, first of all, we had one body. Okay, and then we had R and little r in SO3 cross R3. Okay, and we had expressions for those in terms of coordinates, and the coordinates we used were theta, x, y. Okay, and from these we were able to produce the velocities, okay, the translational velocities in the two versions of the angular velocity, spatial and body. We had the inertia tensor about the center of mass, okay, and that was stuff which didn't matter, and then some number down in the bottom right corner. All right. Okay, so then with all of that, we can calculate, or we did calculate, it's not much of a calculation, the kinetic energy metric, G. And I think I have a feeling I called this J, so let me continue to call it J, was J d theta plus M dx plus dy. Okay. All right, and then we were able to calculate the Christoffel symbols. In this case, they're all 0 because the components of the kinetic energy metric in these coordinates, which are J and M, are independent of x, y, and theta. Okay. All right. Then we calculated some forces and torques. Okay, so we had a force that we applied here at this point, which we called had some magnitude capital F. And then we had a torque, let's call that magnitude T, that we apply there. And so we calculated the Newton-Euler versions of the force and torque. So F as the force, which we translate to the center of mass, is F cosine theta plus phi, and F sine theta plus phi, 0. And then tau was T in the Okay, and then we had to translate. So we did this all last time. Translate the force to the center of mass, and in doing so, there's an induced moment, which was F H sine sine phi. Okay, and phi was that angle. Okay, and H was that distance. All right. All right, and then this is again what we did last time. So we calculate the Lagrange force, and I'll call that capital F. And so, you know, I'm going to just go ahead and abuse notation here, and use F for the magnitude of this force and also for the Lagrange force. Okay, so if I were typing this, I would use a different font, but I don't want to call it something other than F. All right, so you get F cos theta plus phi dx plus F sine theta plus phi dy, and then plus t minus F okay, F H sine phi d theta. Okay. All right. So, you know, there's a lot of stuff to grind through here, but it's all, especially for this example, it's all straightforward. And then the only other thing we need to write down the forced geodesic equations. Remember that the forced geodesic equations involve G sharp. Okay, so let me write the forced geodesic equations here, since that's what we're going to write down. So the forced geodesic equations remember what they look like. They look like the equations for the geodesics for the Levi-Civita connection equals G sharp F. Okay, and so the only thing here that we don't know is G sharp. Okay, and so in coordinates, these equations look like Q double dot J plus gamma G J K L Q dot K Q dot L is F J K. I'm sorry, not F G. F K. Right, and so it's this thing that we don't know, and we get that by, remember that last time we talked about it, to get G super JK instead of G sub JK. So G sub JK are the coefficients that we read off here. G super JK is the matrix for that is just the inverse of the matrix for G. Okay, so let's calculate that. Again, this is an easy calculation in this example. So G is, okay, according to our coordinates. And so I've chosen to order my coordinates as theta x, y. So I should write down G according to that order. So that means I should get J here, M here, M here, and everything else is 0. Okay, the inverse, which are the components of G sharp. Okay, so that's a reasonably straightforward matrix to invert. Okay, all right, so finally, I have all of the data that I need to write down the equations of motion. All right. Okay, so all right, so that just means that I'm going to write down those equations with all of the stuff that I wrote down above. Okay, so this is the matrix here. F is that whole thing. Okay. The Christoffel symbols we decided were 0, and then these are just double dots for the coordinates. Okay. So finally, so the forced geodesic equations are, okay, so it's going to be x double dot, okay, and then there's the terms involving the Christoffel symbols, and those are all 0. Okay, so the only stuff I have to give a slight moment's thought to is this. And so this is just matrix vector multiplication, right? So this means take this matrix and multiply it by this vector. Okay, and so this vector, keeping in mind that we have to order the coordinates correctly, so this will be the first coordinate component of the vector, the second and the third. And so I'm just taking this matrix and multiplying it by the vector with those components, right? So in the x direction, okay, I'm going to get just m times the coefficient here, which is that. So it's f over m cosine theta plus phi. Okay, does everyone see that? Okay. All right. Y double dot in similar fashion is f over m sine theta plus phi. And finally, theta double dot is, okay, so in this case, it's going to be 1 over j, because I'm working with the theta component, and then the theta component of the Lagrange force is that. Okay. So it is t over j minus f h over j sine phi, and sorry, that's it. Okay, right. So those are the equations of motion in this case. Right now, I think it's true that you could probably have written those down in week 1 with a lot less time spent thinking about it than we had to do here just now. Okay. These are simple force moment balance equations for a simple planar rigid body with standard forces and torques applied to it. So that's, you know, going through all of the stuff we went through to get to that point for this example is definitely overkill. Okay, but nonetheless, there it is. All right. All right, so the next example, you know, and we've already seen this when we looked at this example previously, that we kind of don't want to write anything down for this example because it's not like there's a lot of coordinates. There's only 2 degrees of freedom. Okay, but G is a slightly tedious thing to write down. Okay, and so we don't want to do it, and I especially don't want to do it, so I'm not gonna. Okay, but I'll go through sort of in principle and tell you what you would do if you had to crank this out by hand. Okay, so we have the coordinates as usual. All right, so again, let me just remind you of all the stuff that we had. 2 bodies. Okay, and so we had calculated R1, R1, R2, R2 in terms of the coordinates. Theta 1 and theta 2. Okay, then, all right, we just have a straightforward procedure. In this case, it was very simple for calculating the translational and angular velocities. Okay, so we had R1 dot, R2 dot, omega 1, omega 2, omega 1, omega 2. Okay, and remember, we need both of these for our procedure because our procedure involves body angular velocities to calculate the rotational kinetic energy, which is where we get the kinetic energy metric from. And then to write down the Lagrange forces, we use the spatial angular velocities, all right? So you need both of those. Okay. So then we had inertia tensors. And okay, and you know these because again these are planar planar bodies. We only really cared about the term down there in the lower right hand corner. Okay, so we got a J1 and a J2 that came out of that. All right. Okay, the kinetic energy metric. G, okay, so now is when I'm going to stop writing stuff down. Okay. Okay, so you get some stuff. D theta 1 tensor D theta 2. Sorry. Theta 1 plus some other stuff times D theta 1 tensor D theta 2 plus even more stuff times D theta 2 tensor D theta 1. Okay, and this stuff, it's not that bad, but you don't want to write it down. And especially, you don't want to invert that, right? It's a 2x2 matrix, so there's a simple formula for inversion, but the determinant is some, you know, thing that takes a line or two to write down, right? And write the inverse of the component matrix for G, you know, that thing appears 4 times, so it becomes messy. Right, and moreover, the Christoffel symbols are not constant in this case. Okay. All right. Okay, so that's good. So that gets us the unforced equations of motion. Then we had forces and torques. So we talked about this last time. So again, we have the Newton and Euler versions, and so there's no forces. There's a torque. Okay. And I forget the ordering I put here, so I think it was, oh, yes, that's right, sorry. Right, so there were 2 Newton-Euler forces and torques for this thing, right? There was a torque T1 there, and a torque T2 applied between the bodies. Okay, so I had 2 forces, and so 2 bodies, and so you have to calculate the influence of the 2 forces on the 2 bodies. Okay, so okay, so the forces are still 0, and then the torque on body on body 2 associated with all right, so what I forget, I'm probably going to get the order differently than I did last time. There's a 2-1 and a 1-2. So I'm going to make the declaration right here. Again, that may be different from what I did last time. So this is the T2 thing, okay? And this is the T1. And then this index here is body 1. Okay, and similarly for that one there, it's body 1. All right, so that's the convention that I'm going to use. It doesn't matter, do whatever is consistent. Okay, so then remember that what I wrote down here were the force torque for this torque on body 1. Okay, then I had to write down the force torque for this, for this torque on body 1. Okay, and so that was 0, 0, T2. Okay, and then we had, sorry, this was 2, 1. And then we had to do the second body. All right, so it was F1, 2 is 0. Tau 1, 2 is 0. F2, 2 is 0. And tau 2, 2 is 0, 0 minus T2. Okay, so we did this last time, and so I'm just rewriting it. Okay, because and remember the whole deal was that you have a torque that's applied to body one, and whatever you do to body two, it'll be the opposite sign because they're interconnected. Okay, and then you write down the Lagrange force, and that was, okay, so if I get it right, I think it was T1 plus T2 d theta 1 plus, minus T2 d theta 2. Okay. All right. So then we have the forced geodesic equations. Excuse me. Okay, so let me write them out again, just so I have them here to refer to. Okay. All right, so there's a bunch of stuff here that I haven't actually explicitly written down. Right, and I promise you, at this age of my life, there's nothing that would ever make me calculate that stuff by hand. Right, and so I'll show you how to do it in Mathematica in just a second. All right, so let me just sort of write down kind of what the equations look like. Okay, so you're going to get some stuff. Okay, so there's going to be some Christoffel symbol stuff. Okay. And it'll look like this. Okay. Then you're going to get stuff which comes from this term, right? So it's going to be the components of the inverse of the components of G. Okay, so that's generally going to be pretty messy. Okay, times the components of the vector F, which are very simple. Okay, so what are you going to get here? Okay, so you're going to get a 2 by 2 matrix, which is that thing. Okay, times the vector with 1, 2 components. Right. So what you're going to get here is you're going to get some ugliness times T1 plus T2. Okay, then you're going to get some more ugliness, and it'll be with a minus sign in front of it, times T2. Okay, so that corresponds, of course, to that, and that, including its minus sign, corresponds to that. Okay, then you have theta 2 double dot plus theta 1 dot squared plus theta 1 dot theta 2 dot, and these things are generally non-zero. Okay, and then the same kind of thing, except you're looking at the different components of the matrix. Okay, so let me maybe just to clarify as much as I care to here, you can sort of you can say that this is G11 and this is G12, whatever that is. Okay, and here you're going to get G21 and then minus G22 T2. Okay. All right, so that's in principle how you go about calculating the equations in this case. Now, I would say that using force moment balance equations like you would have known about from first year physics for this example, it's probably, unless you have lots of practice with that stuff, you probably get it right after a little while. But you probably, if you're like me, at least you'd mess something up the first 6 or 7 times through, right? And that's one of the advantages of this approach, which I'll now sort of show you by, oops. Oh, okay. I'll show you by looking at some Mathematica, okay? All right, so here's a Mathematica worksheet. So sorry, I'm gonna do the screen share here too. Okay. Okay, good. Okay. All right. So this is the gyro example that you've been looking at on homework. Okay. All right. So I guess you're familiar with this. There's 3 bodies. There's the sort of platform. There's the frame that holds the which is attached to the platform and which holds the sort of gimbal setup, which runs across here. Okay, and then there's the rotor, which rotates inside the gimbal. All right. Okay. Right. So let's go through and do Mathematica on this. All right. So I have little functions here to define the hat and the check maps just for convenience. So I don't have to remember them. Okay. All right, good. All right, so I'm going to also sort of describe a little bit how you do these things in Mathematica too. And so the coordinates are theta, x, and y. I want to specify theta as being a function of t. And the reason I want to do that is because you'll remember that to calculate kinetic energy and to calculate the Lagrange force, you need to have r dots and little omega 1 and big omega 1, and those involve time derivatives. Okay, so the way I've defined the coordinates, I've made them functions of t, and that's how you do that in Mathematica, is like in square brackets. So now I can, differentiate those with respect to t. Okay. All right. So which I will do now. Okay. And so you see that the notation looks like what you expect. Theta prime of t. All right. So so that's the coordinates. And then what we do is we write down all the big R's and little r's. Okay, so there's 3 bodies for this system. So I have 3 R's, 3 little r's, and 3 big R's to write down. And I'm going to index them, right? So it's going to be R1, somewhere down there is R2, and so on. Okay. Now for each body, I'm strictly speaking, to do this in the way that we do this, the body frame could be at the center of mass. Okay, I've drawn it here in this diagram to be at the base, but here in my Mathematica, I seem to have kind of put it at some height, which would be the center of mass. But it doesn't matter. Why doesn't it matter? Why does it really absolutely not matter what R1 is? That's right. So there's whatever it is, it's not moving. Okay. So yeah. Okay. Then we had a capital R1. Okay. So this is now kind of a process that we're quite familiar with in determining body frames in terms of spatial frames. Okay. So there's big R1. Okay. And if you want to see things in the form of matrices in Mathematica, that's how you do it. All right, and R2 is the same, right? So the center of mass of the gimbal that holds the disk that doesn't move. Okay, as long as I'm assuming that the center of mass is kind of at this point right here. Okay, if it turned out that the center of mass was located here for some reason, which is not just so incredibly awful, then you'd have to bookkeep that. right? But it turns out in this case that thankfully this velocity is 0, so that simplifies some things. Okay, so then we calculate the big R2 and the big R3. And we did this by first writing our big R2, not in terms of the spatial frame, but in terms of the body 1 frame, okay? Because that's just a little bit easier, okay? And keeps you from possibly making mistakes, okay? So there is R12, okay? Right, so that's the body frame for body 2 relative to the body frame for body 1. Right. Okay. All right. And then now to translate that into the body frame for body 2, I need to move it into the spatial frame, and I do that. And so you have to think a little bit about the order in which this multiplication happens and whether you're transposing stuff or not. But when you think about that, that's what you get. Okay, so that's R2. All right, so I've just taken the frame relative to body 1 and moved it into the frame relative to the spatial frame. Okay, so that's what R2 looks like. All right, so again, making standard assumptions about sort of centers of mass and stuff. The center of mass of the disk should be at the same place as the center of mass for the gimbal, and that's reflected right there. Okay. And so we do the same kind of a trick for R3, right? We're going to write the body frame for R3 in terms first of the body frame for R2. Okay, so that's a direct calculation, which I do there. Okay, that's what it looks like as a matrix. And then just like above, you convert it into the spatial frame. Okay, so this one is relative to the body 2 spatial frame, and this one will convert it into the spatial frame. Okay, and so this one gets a little bit ugly. All right. Okay, so now what I will do is calculate all of the translational and angular velocities. Okay. All right, so the translational velocities, and so now is where it's convenient because I've indexed all of my little r's and big R's with a 1, 2, or 3. And so the translational velocity is the derivative. This is this thing here reads RA dot. Okay, so that's calculating all of the translational velocities. And then similarly, I have the angular velocities, right? So the capital omega here is body angular velocity, right? So that's the formula for the body angular velocity. And so it's R transpose R dot, right? And then I unhat it. Okay, so for an example, there's one of them, but I don't even need to look at these. They're all just kind of stored. All right, and then spatial angular velocities, the same thing. Okay. So then you have inertia tensors. So notice that after figuring out what R1, all the little r's and the big R's are, calculating angular velocities and translational velocities can all just be done automatically. This is another not automatic step, right? This is one that requires some human input. And so the frame here is rotating, but it's planar, right? So the frame rotates about the spatial S3 axis, which is also the body 1 3 axis. And so I can, without loss of generality, assume that the inertia tensor looks like this, and I don't care what these A's here are. And in fact, as we saw in class, you could even take these zero terms here You could even make those non-zero and it still makes no difference. Okay. And so that's the inertia tensor for body one. Now, what about body two? Okay, so body two is the gimbal here. Okay, so a reasonable assumption, I think, for that is that it's going to have three principal inertias, one about each of its own body axes. Okay, so it's certainly going to have, you imagine, a principal inertia about its body two axis, and similarly the body one, body one, and sorry, I meant to say body three here. So the body two third axis, the body two second axis, and the body two first axis, right? Okay, so think of that as being like a rectangular kind of a thing, maybe. All right. So it is there. Okay, and so you see that it's diagonal, and its diagonalness is exactly a consequence of the fact that I've assumed that the body axes for body two are principal axes. All right, now body three, okay, so body three is a disk, okay, and so for disks, you can, it's sensible to say that in this case, the axis which is orthogonal to the plane in which the disk sits is an axis of symmetry. Okay, and so what that means is that the other principal inertias, that'll be the B32 and about B32 and B31, are equal. Okay, and then I have some other principal inertia in the third direction. Okay, so that should be reflected here. See, so it's J31 and J31 in the B1 and the B2 directions. That reflects that the B3 axis is a body of an axis of symmetry. Okay. All right. Okay, so again, that's a place where you have to do some thinking. And then we go through quite a lot of stuff where you don't have to do any thinking. So we calculate the kinetic energy, right? So for each of the three bodies, I calculate its kinetic energy, right? So it's 1/2 mv squared. And this is the way you take the Euclidean inner product of vectors in Rn and Mathematica is by putting a dot between them. It's a more general operation, but in this specific case, it does that. Okay, and similarly for, so I get the rotational kinetic energy done using the body angular velocities. Okay, then I can calculate the total kinetic energy. All right, and so when you simplify it, it's not that bad. Okay. And then you can grab the kinetic energy metric, the matrix form of the kinetic energy metric, and we use the formula that I gave you in class for that, which is that you calculate the matrix. You have the kinetic energy, which is a function of all the velocities, the q dots, and you calculate the matrix of second partial derivatives. That's what that is. Okay, and then so I've done this. Actually, I think this is the first time I used the table command. The table command is what you use in Mathematica to create arrays. And so you can see here, there's two indices on this array, J and K. So that creates a matrix, a table with two indices. Okay. All right. And so when you simplify it, you get this, which again isn't so bad. And in particular, well, it's not quite diagonal. All right, now is where things become a little bit unpleasant. So you invert this. Okay. Whoops. Oh, sorry, I didn't hit enter on that, I guess. There we go. And so again, as I mentioned in class, the thing that makes this not fun to look at is really just the determinant appears in a lot of different places. And so one way to, if you need to display the kinetic energy metric, one way to do that is to calculate the determinant and then multiply the inverse by the determinant. And that gets you something a little bit, doesn't have all the ugly denominators in it. Okay. Okay, Christoffel symbols. right, so this is now Mathematica calculating Christoffel symbols. So let me try to parse this all for you. So first of all, the Christoffel symbols are going to be put into a table with three indices on it, right? Corresponding to the fact that it's gamma I, j, k, or I guess here I'm calling it gamma MKL. All right. Okay. And so then you get the formula, which is G super JM. Okay, so that's that bit. Okay, and then I get all the derivatives, right? So the components of the derivative, GMK partial derivative with respect to QL, DML partial derivative with respect to GK minus the GKL partial derivative with respect to QM. Okay, so it's the usual formula that we're used to. Okay, and so it's a little horrible. All right. Okay, now forces and torques. Okay, so what I'm going to do is I'm going to apply a torque down here for body one. Okay, that's going to forcibly spin the thing, the whole assembly about the spatial S3 axis, and then I'm going to have a motor, let's say, between the gimbal and the disc, which spins the disc. Right? Just as a example of the kind of thing I might do. All right, so the first thing you need to do, all right, so that means there's two kinds of forces, right? And so I have to bookkeep them all. And so, all right, okay. So, yes, okay, good. So the force component, of course, so I didn't do this as systematically as I would have liked to, as I look at it here, because I've just done it for each body, right? Body one, body two, and body three. I didn't break it down into force one on body one and so on, which I think is sort of a more systematic way of doing it. But and the reason you can get away with it in this case is that the torque one only does stuff to body one, right? And the torque two, the torque two for the disc, it only does stuff to body three. And so I don't have to bookkeep what it does to all the other ones. So you can get away with it in this case. But sometimes when there's interactions between forces on two bodies, you should be more careful about that. Okay, so in any case, there's the force corresponding to the torque, which of course is zero. There's the torque corresponding to the torque about the S3 axis. So I've applied no forces and torques to body two. Okay, so can you sort of understand why the torque that I apply to the disc doesn't have a component in the body two direction? Why is that? Why? Because there's a motor between body two and body three, but I'm not bookkeeping that. Why am I not bookkeeping that? Yeah, that's right. The work that force does on body two as you undergo an admissible motion will be zero. Yeah, and that's for the reason that you just said. Okay. All right. So again, I kind of just luck out here. Okay. And then there's no force on body three, but there's a torque. Okay. So the torque is about the body three, B3 axis. Okay. But I need for torques and forces to be applied about spatial axes, not body axes. So I have to convert the B3, the B3 axis into the spatial axis. And the way you do that is you multiply the vector by the vector B3, which is 0, 0, 1, by the matrix R3. And so what you get is just the first row of the R3 matrix, okay? Okay, all right, so then once you have the Newton-Euler forces and torques, then you write down the power. right? And so again, the power is just, summing forces times velocities and torques times angular velocities, okay? And it turns out to be quite simple in this case. All right, now to calculate the Lagrange force, what you do is you take the power, okay? So the power is this expression right here. Okay, and I know kind of on paper how I do that. I read off the coefficients of the velocities, right? So the velocities are, so I named my coordinates up here, theta, phi, and psi, okay? And the components of the Lagrange force are going to be the coefficients in this expression of theta dot, phi dot, and psi dot, okay? So, there's theta and psi dot. And the way you do that in Mathematica is you use the coefficient function, right? So you give it the expression, power, and then the thing whose coefficient you want, which are in this case the velocities, and and then you put them in a table, and you get out the components of the Lagrange force. Okay. All right, then there's the equations of motion. Okay, so the equations of motion are q double dot, right? That's what that is. So that's the time derivative of q dot. Then you get the Christoffel symbol business, which is all of this, right? So it's gamma jkl q dot k q dot l summing over k and l. Okay. Then I get the G sharp F part. Okay, so that's the matrix, which is the inverse of the kinetic energy matrix, times the vector of components of the Lagrange force that I calculated up here. All right, so you just plug that in there, and there's your equations of motion ready to stick into a program that will do numerical simulations. Well, Mathematica will also do that. Okay, and so there's two reasons I wanted to go through this. One is to sort of show you how you do this in kind of a systematic way. But the other thing I wanted to emphasize is that, as I said last time, there was only 3 places where we gave inputs to this system. One is writing down the big R's and little r's. Okay, one is writing down the inertia tensors, and then one is writing down the Newton-Euler forces and torques. And those things generally aren't that bad. Certainly computationally, they tend not to be that bad. And all the computational ugliness is just purely automatic. Okay. All right. Any questions? All right. So as you know, that Mathematica worksheet is on the course webpage. Okay. Yeah.
Do we have to do it by hand for the project?
Oh, no, definitely not. Yeah. Other questions? Okay, good.